Welcome back, everybody. I think what we'll do is we'll talk a little bit today about Sharp test priors and then the connection between base factors and posterior. So I'm going to exchange this order to show you something that's general right here, but I'm going to try to motivate it through this prior. So let's just start up there. So any questions about p-values before we begin? My assumption is you've all computed one or seen one once upon a time, and if you haven't, you never took the prerequisite. Some inference class would make you do that. So if you've never seen a p-value, you've never studied science. So it seems to be one of the baseline non-measures that people invoke to decide whether or not the results are meaningful enough to publish. That trend is going away. So I'm going to post probably later today, and we'll discuss next time. There's been a ban on p-values in some journals. So some people are getting farther and farther away from wanting to accept these things to the point of actually banning them. ASA has made comments on that. That's the American Statistical Association, and we'll discuss their commentary as well, what their stance is. I do mean it in the they sense, not a me included in the global they or whatever. So I don't agree with their I would say their cowardliness. So unfortunately, it's hard to get a lot of people to agree. So what people will do is they'll form committees, and they'll dilute their opinions so badly that it doesn't really represent anybody. So this is typical politics. Anyway, I think that the era of just having a p-value less than 0.05 and considering that meaningful is going away. And one of the reasons is this example that I showed you last time, where I computed the z-score. We said this was just x bar minus theta naught over sigma over root n. And I said something about this is xn, the limit is n goes to infinity, x bar n, that goes to true theta, that's the truth. So that's always true. So we like the average because it tends to the true average. So maybe you've heard this before, the expectation, the mean of the mean is the mean. So this is the mean in our model. We're still discussing theta as the Sharp test scenario in the standard normal model, where xi's are coming from a normal, mean theta, sigma squared over n. So the expectation of the empirical arithmetic average is the true mean. And sometimes I like to say the mean of the mean is the mean. And that is true. So, but I'm using the word mean different in every case. Expectation, arithmetic average, true mean. So that goes to the truth. If this thing is equal to, let's say, 1.96, and I'll put the absolute value sign on there. So it could have been negative, it could have been positive. Basically, we're looking for some deviation. If that were true for n, as we climbed all the way to infinity, so I'm invoking a concept. And we will reach a contradiction out of this. So we know that xn minus theta naught is not exactly, xn isn't exactly theta naught if this was true for finite n. It would be 1.96 standard errors away from it. But if I take the limit of that idea, we know what the denominator converges to, it's 0. So for that to converge to something finite, the numerator also has to converge to something finite. It needs to converge to 0, and it converges to 0 1.96 times faster than the denominator. So if you like asymptotic arguments, what this really says, if this is going to be fixed, 1.96 that relates to a p-value of 0.05, then it means that xn minus theta naught is tending towards 0. So that means if this thing is tending towards theta, then theta is equal to theta naught. So in the limit. So if you like limiting arguments. If you don't like limiting arguments and they confuse you, welcome to the club. So nobody really understands this infinity thing because it doesn't really happen. So, but anyway, just in terms of that, this would just be absolutely close. Now I would agree with somebody if they said they had a fixed n and they went through a lot of trouble to specify what n would be meaningful, i.e. they would calibrate their power in a test, and then they would go and collect exactly that much data. That might be a meaningful way to do things. So would it be meaningful that you're one standard error away from something, or two standard errors away from something? That's up to your subjective criteria. So when they were trying to find the Higgs boson, that particle, they were trying to measure something that was non-zero. They said that they needed to measure something that was like at least 6 standard errors away for it to be meaningful. So why 6? Well, they came up with that criterion. They probably mapped it over to some probability and said that they were like very, very sure about things. But keep in mind, if they're thinking about a p-value, they're really just calibrating error rates. And I think in an experimental design where you have control over everything, that can be meaningful. But at the end of the day, you're probably not going to take this number to be the meaningful number. So if your question really is something exactly 0 or non-zero, maybe you can use this setup in an experimental setup. But in general, if you're just collecting data out there, and you just look for bigger and bigger n until you get significance, it's going to happen for you. So, and that's not a meaningful way to do science. I think you have to pre-specify what your tolerances are, how far away this thing needs to be from theta naught before it's meaningful to you. So, anyway, take from that what you will. Let's think about how Bayesian approaches all of this. So same test setup. So xi's come from a normal, mean theta, variance sigma squared. I think I put maybe an n under this, but I'm not sure I meant to. I can see it down there, so you can erase that n from everything. So h naught, theta is equal to theta naught. The alternative is theta something different. I think we all agree what we need to decide is how far away it needs to be from theta naught before we think there's a meaningful difference. We have to think about what that actually means. I.e., 1.96 standard errors, to me, it really depends on what your sample size is. If you tell me you have 1 billion data points and you're only 1 standard or 1.96 standard errors away from the null hypothesis, I wouldn't take that as meaningful because I would understand that's epsilon. That's something really tiny. And I would ask you if you've really thought about that. Is that a meaningful difference to you? And I think in a lot of cases, the answer is no. It's not meaningful. So what have people done? They went and just collected lots of data so that they could call something meaningful that they don't think is meaningful in the first place. Don't think that's reasonable. What did they get for it? They got published. And I don't think that that's necessarily the end game. For some of you, it might be, and you can decide who you are. So I'll be able to tell when I read your academic papers in 20 years. You can also read mine. I've been in the game for about 20 years. I've reported p-values once or twice. You can decide whether or not I did it in a meaningful way. Okay, so Bayesian is going to do this. We already know if we used a continuous prior to test this hypothesis, we'd construct the posterior, and then we would measure how much mass is at theta naught under that continuous posterior, and it would be 0. And so we don't want to test this explicitly. We need to say something a little bit different. So here's what we're going to do. We're going to think about our alternative, and we're going to think about our null separately. Now there's only one way to smear mass over the null. So it's just defined at a point. In the alternative, there's lots of ways to smear mass, but I want to introduce you to what is called a point mass prior. So point mass priors look like this. And this is the typical thing Bayesians will work with to come up with the posterior probability of that null hypothesis. So they look like this. So I'm going to say pi theta. So that's my prior on the entire space of theta. So the null and the alternative. So theta can either be in the null space or it can be in the alternative space, i.e. theta is either theta naught or it's something different. So this is the whole universe of theta, so the whole real number line in our example. And I can write down a prior like this. So I'm going to write down my posterior probability. I'll write it maybe like this. H naught theta plus 1 minus pi naught. And I'll write down prior probability on the alternative space. So let me tell you what this all means. So this is the probability that H naught is true in the first place. Prob H naught is true a priori. And we haven't really discussed this parameter yet, this part of the prior. This is how we smear mass in the null space. These are our weights on theta in thetas belonging to the null space. You can probably decide what that is. Again, there's only one way to do it. So I'm writing things down a little bit overly generally for our first exposure to this. Following that, what's this? How would you interpret that? Scribbles on a chalkboard? Probability that the null is not true, right? It's just probability theory. And all Bayesians just follow probability theory. So the probability that the null is not true, and in our dichotomous world, only two hypotheses, that says something about the alternative. What does it say about the alternative? The probability that the alternative is true. Child's play. Probability that H alternative is true. And so, i.e., probability H naught plus probability of H alternative. If this is just two disjoint sets, they are. And that's the whole collection of everything. I know what that adds up to, 1. And that's what we've just done. So I've got pi naught plus 1 minus pi naught is equal to 1. And so pi naught is some positive number that lives between 0 and 1. And this is how we're going to smear mass. We're going to weight thetas in the alternative space. So weights on theta in H alpha, right here. So if I'm going to test this right here, so this is my space in which the null lives, i.e. theta is equal to theta naught. There's only one way to even define this, if this is going to be considered like some sort of a probability density, if you will. So for testing H naught, theta is equal to theta naught. So again, everything just happens at a point. There's only one way to smear mass. This is just the delta function. Theta is equal to theta naught. So this is just a 1 if theta is equal to theta naught or 0 otherwise. Now I do understand, I called this thing a density and I thought of it as a density. So in terms of a density, this would have to be infinitely high if I thought about it as a density function, and if I integrate it across that point, it's 1. It's all the area under that mass. So you can take this limiting concept of an actual probability density function, and I can integrate over that, the area under it is 1, and if I collapse the variance on it down to 0, that's going to limit to this function. I'm not going to take you through the understanding of a delta function where it's got infinite mass. If I integrate under it, that is going to be 1. I'm just going to state it. Okay, so for you that like measure theory, I've just taken a quick shortcut. So it's really just this right here, theta naught. I've got this mass right here. And you can multiply it by any constant if you like. So, but it's really just the density form of it is infinitely high with 0 limit. So what does that limit to? I'm saying that the integral under it is 1. So that's what that point mass looks like. This is a point mass on theta naught. If I try to smear mass over this in a different way, I'm just left with this. There's only 1 point. It needs to integrate to 1 under that 1 point. So there's only one way to do this. And that's what I've been saying over and over again. The more interesting question is, what is that right there? And so the question is how do you smear mass under the alternative? And this is a hot question. So there's no one answer to this. There's lots of answers. It's things that people usually don't like to think about when they're doing an analysis. But I'll just point out, if this integrates to 1 right here, and this is a proper prior, that'll integrate to 1. Then I have something that integrates to 1, this integrates to 1, that's the only place the thetas appear in all of this. And then I add it up discretely over the two things. This whole thing integrates to 1. And so if this is proper, then this whole thing is proper. So it's just a weighted average of 2 spaces. So what the Bayesian is doing is they're thinking about how to average things over theta, but then they're taking an average between their 2 hypotheses themselves. A lot of people like to focus on this right here, and they think that maybe Bayesians are steering their analyses by talking about this. If you ask a Bayesian in a colloquium how they chose this parameter, they'll always give you a reasonable answer. So they'll probably say something like, oh, I picked it to be a 50/50 on both spaces. And nothing more to ask about. The real question is, what is that? So what a Bayesian is going to always do is they're going to compare their null to their alternative. Keep in mind, everything in the null space and everything in the alternative space adds up to 1. So everything's on a probability scale. So they're automatically being compared directly against each other. And that's one of the big differences between what a Bayesian does and a non-Bayesian. So a non-Bayesian isn't doing a comparison against the alternative. They're calibrating error rates, which is different. The way those errors behave in the 2 different spaces is different. So real question is, how would you pick this? So let me just state something that maybe we want this to be conjugate. So this might be the conjugate form. And then I would have 2 parameters that I need to pick. Now the conjugate prior isn't the only prior going. And in fact, when I do this, I don't use conjugate priors. So I do something a little bit different, and I'll tell you more about that later. But we're not going to be able to describe anything analytically unless we work with the conjugate form. So I will say this, asymptotically, using the conjugate prior and the thing that I might do in an actual analysis, truth be told, I would avoid this analysis at all costs, unless I was forced into doing it, where it's like, oh, we really do need to make a decision. There really is a decision. I'm going to program a robot with this, and the decision's going to be made. So, but if I were doing scientist and sitting down with a scientist and they conjectured this, I would try to talk them into either a prediction problem or an estimation problem. So I think that those are more meaningful. What I would do would at least asymptotically agree with what this would do. So if you like asymptotic arguments, the thing I'll tell you about later that's a little bit more complicated, and I think it makes sense, but you need to do MCMC to work with it. You can't do all the math up front. So I want to do something where we can at least do the math, and then I'll tell you where the issues are with it. Very often what I'll do is I'll take that to be a Cauchy also, and I'll let it have Cauchy tails. You already know how you can change a normal into a Cauchy in one step. So they integrate over the precision parameter. I rescale the precision parameter and I integrate over that with gamma weight, where the gamma is gamma half-half. Okay, so if we all accept that maybe using the conjugate analysis will make everything easy and we can at least start with that as a starting point, and a lot of people end with that, that's our ending point too, then we can proceed. So we'll at least make everything a little bit easier up front. So I don't think there's any huge controversy in doing this, but there are issues. If you were going to pick the conjugate prior for the alternative prior, how you smear mass over theta, how would you center it? So what would you pick this to be? So let's change the problem and say temporarily theta naught is 0. So we just have an example in our head. So I want to test whether or not theta is 0 or not. So if I'm going to compare this thing and I really think it might be 0 or something else, I should probably center this at like 10 million, right? So that makes a lot of sense. So if I pick the number 10 million, I'll do 10.2 million. So if I ask this question, I can basically turn it into, oh, it's 0 or something huge, right? No, that doesn't make any sense. Why would I test 10? Why would I do that? Why would I test things around 10 million to compare to if I really actually thought theta was 0? Probably wouldn't want to compare to things that could be 10 million or 10.2 million. It's extremely different. That's a weird comparison to set up. So I think theta is 0, therefore I'm going to compare it to whether or not it's 10.2 million. I don't think that makes any sense. So this would be really bizarre if this was the question you were asking. So where might you center it instead that makes a little bit more sense?
Theta hat.
Theta what?
Just hat.
Theta hat. What's theta hat?
I guess X bar.
You would center it at X bar? Okay, so let's talk about that for a second. It's an interesting answer, centering it at X bar, and I'm not going to say nobody does that out there. So there are some empirical rationales for doing things like that, but you need to be careful. So let's just, there is a conversation I could have with you about empirical Bayes, and maybe you would do that. Let's not quite have that full-blown conversation right now, but let's just go back to an earlier conversation. That if we were going to try to estimate theta, so this is just a side, so I'm going to do that. I'm going to come up with my likelihood function. We know what that is. We could write it down for this problem. It's all just normal stuff. 2 pi square root. I'll do sigma squared, sigma over root n, e to the minus 1/2 x bar minus theta squared over sigma squared over n. Then I need to multiply by some prior. So we know what the likelihood looks like. It looks like this. It's centered around x bar. If you ended up saying a priori, if you pick this to be a normal, and you centered this around x bar, and let's say you were even cheekier, and you said sigma squared over n, and you cheated even further, what would happen? You have this likelihood function, that's what the data is telling you. If I work with this prior right here, that would be this prior. Exactly the same. What do you think the posterior would look like? Who thinks it would look like this? Who thinks it would look different? It would look like this, yeah. You guys can work this out. It would look like that. So we would tighten it up. So keep in mind, the posterior would look like this shape right here if I used the flat prior. So if I used the flat prior, I'd get back that posterior that looks just like the likelihood. If I took a prior and I superimposed it, and I multiplied all those things in there, you could just do this with a quick, on a grid, multiply, square all those points, show what all those points look like. As they get closer to 0, they get pulled down even further. And if they get big, they get pulled up even higher. So that's what you'd be doing if you use the prior was exactly your likelihood function. And it would tighten everything up. And so this is what would be the analysis, is you would end up coming up with your 95% intervals would be something like this. If n was big, it would be really tight. So your 95% interval would say, yeah, I think it's x bar and I'm really certain. Think about what the Bayesian rationale would be. A priori, you think this. It's centered at x bar, and it has variance sigma squared over n. I'm really sure about that. I go and I collect data, and it confirms that for me. But you didn't go out and collect data. You used your data to do that. So what you're saying in a Bayesian analysis like this, where you just plug these things in, is you're saying, I beforehand believe it's centered at x bar. With this type variance, I go and collect data, and it says, yeah, I believe that too. And so you become extra sure. So that's the sequential update. What you keep seeing is the same thing over and over and over again. You become more and more sure in the Bayesian analysis. So this, I think, is cheating. So that's cheating. Does that kind of make sense to do that? Of course you got tighter intervals. What you're saying is you've seen that data before, and essentially you've seen twice as much data than you've actually seen. So that's a cheat. So this is a violation of the likelihood principle. So when we come up with our priors, we probably shouldn't go and grab our data and shove it into our prior, and then take that same data and shove it into our posterior distribution. Now there is something that people will do sometimes. Well, they'll take a subset of the data and they'll calibrate exactly like Sam said. In the subset of the data, but you can't use that data again in the likelihood. And so those are more empirically driven priors. So there's a class of priors for this sort of problem called, there's fractional Bayes factors, there's intrinsic Bayes factors, and they all dip into the data somehow. But you don't use the exact same data, you don't use it twice. If you use the data in your prior and your likelihood, you'll overemphasize how certain you are about things. So I think that there is some rationale for doing that, but not directly. So let's not do that. If we plug it in at x bar right here, we'll become overly certain about something that maybe we're not that certain about. Kind of see what the issue is there? So, let's think about the original problem. We want to test if theta is theta naught. So where would you center the alternative? Theta naught. I think theta naught. So if we were testing theta was 0, theta naught was 0, then we'd probably want to center our analysis at 0, the alternative. I think that makes sense. So I don't know if I want to stack all that mass right at theta naught, and that's the conversation I'll have with you later about the asymptotics of this choice. But I do like that it's symmetric around theta naught. And so if I'm far away to the right or far away to the left, it kind of means the same thing. And that's the question that we're asking. So I think it makes sense to center things. Just to give you a heads up, this prior right here is going to look like this. Right here. So if I take this part, that's that part, and I take this part, and that's the point mass. Right there. This prior that we're forming is a mixture with the point mass, and that's where it gets its name. Just as a heads up, some of the other priors that I'll tell you about later, just so that you're aware of them, will agree to stack mass. They'll put the point mass right here, and they'll do something like this. Where they'll come up with a prior, an alternative prior that's centered at theta naught, and it has some little trough in here. And the idea is that you don't stack too much mass right around theta naught all on the alternative space, because the alternative space, when you do this, is putting a lot of mass right around theta naught. You can remove that 1 point theta naught from this alternative prior. I never do it, just because when you integrate over a point, it doesn't do anything. So if you'd like to remove that 1 point theta naught from this prior specification, you can do it. And if you operate with an actual normal, it'll be exactly the same. Let's come back to this later. These are called non-local priors. Usually the tails have Cauchy behavior to them. And you still need to define what that trough is, how wide it is. So the rates of convergence to the null and the alternative a posteriori are different using these different priors, but what they converge to will be the same. So we'll talk about that later. I think that it makes sense to center your prior around theta naught. And I think it makes sense for at least these early lectures to use this normal prior, because at least we can work out analytically what happens and compare it to a p-value. Okay. Reasonable, unreasonable. So I'm just asking about the theta naught. If you think that it's something else, you're probably going to have to spend a lot of time explaining that to us. And you should center it somewhere other than theta naught. I think that's reasonable. I think this is reasonable because it makes our analysis easy. So we can at least explain some things. And the big question is what's that? Right here, what's this variance in everything? So psi squared, we'll call it. And the question is how do we think about this? Psi squared. So let me just ask you a question. Do you think that should be big or small?
I think it should be big, but proportional to your certainty about theta naught.
That's interesting. Yeah, so it should be bigger than sigma squared over n, is what you're saying?
Are we still assuming we know sigma squared?
We are assuming we know sigma squared in all of this.
I would say yes.
So that's interesting. Eric says it should be big with respect to sigma squared. And you might be able to define how big that is. I think that's a reasonable answer. Let's come back once we work through the full calculation and see what matters. Leave it in as a variable and see what happens. I think that's a reasonable answer. How big? You're talking like huge? So like 4,000 times sigma squared?
I think it depends on the problem.
Maybe.
And the information you have and the forms theta naught.
Yeah. So it has something to do with how far from theta naught you would need to be before you're willing to reject theta naught. And that's the whole thing right there. So this is the alternative variance. And this is where most of our conversation is going to center. So it's how we come up with that in the first place. But it kind of informs how far from theta naught we need to be in order to reject it. If that doesn't make perfect sense to you, we'll work through the calculation and work through the posterior probability, come up with an analytical expression and take the limit of that thing, and we'll see what happens as we move around psi squared. So we'll play around with this example for a couple days. But that's essentially what this is doing. And so I think the whole question when you see a Bayesian do an analysis like that, it's always this. And when I ask people, how'd you pick the alternative variance? If they say something to me like, oh, well, I looked at the precision of what I was measuring, I looked at a bunch of measurements, I calibrated my machine, and I picked a value that I knew that, you know, if we saw values out there, it wouldn't be because of the machine precision, my instrument measuring tools. I would go, oh, cool, okay, that makes sense to me. So you picked it meaningfully. If they say something like, I picked the 1. That seemed reasonable, you know? I don't believe anything in their analysis. So I will tell you this is a lever. right here, and I can steer the posterior probability of the null between 0 and 1 by moving that lever. And if I take this to be infinity, I'll say I need to be infinitely far away from the null before I'm willing to reject it. So if you take this to be huge, and you get posterior probabilities of the null being close to 1, I'll go, no surprise. That's what happens. So this is a hidden lever in all analyses, and it needs to be paid attention to. I think there's also some conversation here that needs to be had no matter what. So why did you pick that prior? But this conversation is probably the more important one. And most people put the conversation here. And it turns out asymptotically, these don't matter that much. Unless you pick them to be like 0.000001 and 0.999999. And if you did that, then people would probably question it real quickly. What I don't see enough people do is question this parameter. So we're going to focus on that. And that's going to be the question. Anytime you see anybody do a Bayesian Sharp test, how'd you pick the alternative variance? That calibrates how far from the null you need to be before you're willing to reject it. So it makes the analysis harder, but I do think you have to think about that question before you even try to attempt to answer a question like this. So one thing I like about it is it forces you to answer that question. And if you're not willing to answer that question, you probably don't have any business doing the analysis. Okay, let's leave that here. That's all I want to talk about right now. So our prior for testing point masses looks something like this. And we'll play around with all these parameters. We'll show what difference this makes. I don't think centering it at theta naught is unreasonable. So we'll live with that because that's the only thing that makes sense, at least to me, and then we'll play around with this. So we'll see what the behavior of these parameters are. What I want to do right now is just show you the connection between a Bayes factor and posterior probability of the null. But let me just show you something in general. In general, this is always true. So, in general, this thing, star, is always the Bayesian prior for testing. Now, when we did the interval test in the one-sided test, and we thought about just forming a posterior distribution and then integrating over that posterior in the range of the null, and we said that's the posterior probability of the null, I was presupposing that pi naught and 1 minus pi naught were both a half, that I was putting equal weight on both those hypotheses. So let's just say for a one-sided test, how would you pick this? So again, we'll go to the same example. So for a one-sided test, we'll do something like this. Theta is greater or equal to theta naught. And the alternative is this. What would you pick this prior to be? We already had this discussion. Did this one. Did it in disguise. Talked about it just slightly differently. We did do this. Can I use the flat prior? Okay. Let's come back to that next time since we're still a little bit confused on that. We'll address these questions, specific examples. The answer for this question, yes, you can use the flat prior. If you think about the Bayes factor, Everything cancels just perfectly nicely in the numerator and the denominator. Let's come back next time. You can use the flat prior for the interval test as well. So you cannot use it for the Sharp test. So let's just make a connection. So in general, if we use this prior scheme right here, then this is going to be the posterior probability of the null. So this is going to be given my data, I'll just call my data x. This is going to be 1 plus 1 minus pi naught over pi naught times the Bayes factor, inverse, all inverted. This is how you go between the two things. So when I was talking about this before and we were doing a one-sided test, we just computed that directly, the posterior probability. And the only thing I didn't tell you is I equally weighted by both hypotheses. And nobody even thought to ask about it because it makes sense that you would equally weight both of them. Especially if you're doing the one-sided test, things bigger than theta naught, things less than theta naught. You don't even think to ask, how much do you want to weight each one of those? But you might have asked, how do I want to weight the thetas across everything? So in that hypothesis, I had taken 1 minus pi naught to be a half. Pi naught was a half, and that canceled out, and that was just 1.
Professor, I'm sorry, is it an elementary calculation to show this?
Yes.
Would you mind doing that?
I don't mind, and that's why it was my plan.
Okay.
So, yeah, why not? So what's the Bayes factor? Lots of ways you can show this. So I want to give you a few different interpretations of Bayes factors as well. You'll hear people talk about these a little bit differently. So what is that thing? This is just going to be the integral of f of x given theta pi h naught theta element of h naught b theta divided by something similar on the alternative space. If you'd like to write some notation that this is pi theta given HA, that's fine. That's good notation. It's pi theta given H naught. That's good notation. And so from this, if you're just kind of following Bayes' theorem, you could say, I'm going to restrict theta because that's all I'm going to touch just to H naught, and I could vary an H naught in there if it makes you feel better. We are integrating over thetas just in H naught, so you could plug an H naught in there if you wanted to, but you're not changing the equation any. So again, you're integrating over the alternative space, so I'm restricting myself to the alternative space. So if I thought about this, what's happening in the integrand is this is just the joint of x and theta. And then I'm integrating over theta. So what do we get? We come up with the margins on the data under H naught. This is going to be the margin given the alternative. So the way we interpreted those was on average, when I'm averaging over the models, the thetas in the models, the things in the hypotheses, this is just the marginal support of the data given the null space. This is the marginal support of the data given the alternative space. So I can think of a Bayes factor as the ratio of two margins where I've marginalized over the null and the alternative space. Of course it matters how you smear mass in there. For the one-sided test, maybe it makes sense that I could use a flat prior here. Any proportionality constant that I introduced up there, I need to take care of it exactly the same way downstairs. They would cancel each other. Okay. Can you see it yet? Using this notation? Let's just see. This is really just Bayes' theorem in disguise. So this thing right here is going to be 1 plus 1 minus pi naught. That's going to be the probability of the alternative over the probability of the null. That's what this stuff is. Now I have the Bayes factor inverse. Flipping that upside down. So this is going to be f of x given HA, f of x given H naught. Invert all that. So again, this is just an elementary calculation. So let me just rewrite this, if you will. I'll get rid of that inverse. Just write this as 1 over, if you will. I'll multiply everything in the denominator by all this stuff down there. And I'll multiply the numerator by that stuff as well. So I'm going to multiply the top and the bottom by that. And so this is going to look like probability of H naught. I'll reverse the direction of these, if you will. Times the probability of H naught. Again, this is just pi naught. It's that thing. Divided by probability, do it this way, f of x, H naught, probability of H naught, these are discrete sets, f of x, given HA, times the probability of HA. Again, what are these margins? They're just the margins that you compute for the Bayes factor. And what's this? I think that's the thing over on the very left-hand side. That's just Bayes' theorem. So this is the probability of H naught given all of our data. So if you do something weird in the Bayes factor and you're using weird priors, then your probabilities are going to be weird too. You end up invoking. So if somebody's talking about a Bayes factor, they're talking about a probability. What they haven't done is they haven't told you what your prior probability on the hypotheses are. So keep in mind, in a Bayes factor calculation, I never use pi naught or 1 minus pi naught. It's not there. So this is just the margin. What I'll hear some people say sometimes when I ask them, why do you like Bayes factors and not posterior probabilities of the null? And this is a common answer. And they'll say, oh, because they're prior free. And it drives me absolutely batty. So they're not prior free. So the Bayes factor used this part of the prior, right here. So these are the meaningful parts. So they're hiding something from you if they say something like that. But there's no pi naughts in there. If you want to convert over to the posterior probability, you need the actual explicit probabilities on the hypotheses. They're usually easy to talk about. In just a two-system case, a half and a half is usually pretty reasonable. It is a lever also, so if you were doing, let's say, regression analysis, and there are a lot of things, probably doing a half on one parameter in and out versus everything else probably doesn't make sense. So you could use it as a lever to regularize your model complexity if you wanted to. We'll talk about those cases probably after we get back from Thanksgiving. Here's another way to think about the Bayes factor. So I could have written down the probability of H naught given X over the probability of H alternative given X. This isn't the right thing. So these aren't equal to each other, obviously. So it's not the posterior ratio, it's the marginal ratio. And these aren't quite that. So these posterior probabilities have the prior probability built into them. That's how they became posteriors. So if I wanted to divide them out, I could do that. So I could write down this. Probability of H naught divided by probability of H alternative. So that thing is just pi naught over 1 minus pi naught. So here's a way to think about the Bayes factor, which is a little bit different. So it's the posterior odds compared to the prior odds. So it's the odds of the odds. So if I think about my prior odds before I see data, I might have some statement about what I expect to say a priori. And this is how much it changes my mind in the numerator. So if I think of this as just one ratio, then this is the odds increase over that. So it's the posterior odds increase over your prior odds. So it's how much the data has changed your mind in terms of the odds. So that's a little interesting to think about. Yeah?
And that's equal to the base factor.
That's equal to the base factor. So this whole thing is the base factor as well. So the posterior odds compared to the prior odds, so it's how much the data has changed your mind on an odds scale. And some people like to interpret it that way. Some people like to think of it as the marginal support on average. How much do you like each model class? Where the averaging's over theta, and I'm talking about the marginal support of the data. I could think about it that way. Or I could compute it over to a posterior probability on the null and tell you how much I favor one on a scale. Favor one over the other on a scale between 0 and 1. So lots of ways you can think about all this stuff. Let's come back next time. I'm inclined to break this up just a little bit. So I think we'll come back, we'll touch this problem, but I also want to introduce you to the interval hypothesis. And I want to show you that the way the Neyman Pearsonians deal with that problem, it's less than appealing. So there's some real problems with it. But basically, the p-value doesn't get bigger or smaller necessarily as I make an interval increase. You might think as I make an interval increase and I'm testing the null of being inside that interval, that if I make the interval increase, the p-value should get larger. And it doesn't do that. It gets smaller than larger. It can do it in both directions. So we'll come back next time. I'll try to introduce you to a paper. We'll talk about what a Bayesian does, and then we'll come back to specific calculations with everything. So we'll actually do the test. We'll try to calibrate everything and show the dependence on that alternative variance parameter. That's it for now, you guys. Also, I do have your homework. So let me pass those back to you.